Our first speaker has spent more than 2 decades building distributed systems and high-performing teams and has worked as a senior technology leader at eBay, Google, and Stitch Fix. He coaches CTOs, advises companies, and generally makes a nuisance of himself wherever possible. He talks a lot, sometimes at conferences, about software, and is interested in the nexus of culture, technology, and organization. He's currently the SVP Engineering at Thrive Market, and the title of his talk, Large-Scale Architecture, the Unreasonable Effectiveness of Simplicity. Please put your hands together for Mr. Randy Shoup.
Great, thanks. It's always exciting for me to be back at Craft. Gerge reminded me that I was here for the second one 9 years ago, and this is now, I think, my 8th, so really excited to be back. This is my favorite conference in the world. So today I want to talk to you about large-scale architecture, the unreasonable effectiveness of simplicity. And the genesis of this talk is really my realization after doing software for a long time that all the things that we do around scaling systems are all about making pieces of the system simpler, right? It's all about making the units, the components simpler, the interactions between the components simpler, and then the types of changes that we make through the system simpler as well. So I hope that you'll kind of derive from this a bunch of principles about how maybe you can scale your own systems going forward. So I want to start, well, first a little bit of background. As Alex told you, I've been a senior engineering leader at eBay, at Google, at Stitch Fix, and at WeWork. And then most recently, I took a job as SVP of engineering at Thrive Market, which is an online organic grocery in the US. So let's start with a couple of architecture stories which are going to kind of motivate the problem, and then we'll talk about the different aspects of simplicity as we scale large-scale systems. So the first example is the example of eBay. So eBay was founded in 1995, and it famously started as a monolithic Perl application. It was just a toy project that the founder did over a 3-day weekend in 1995. Every item was a file. It just ran on his, I'm imagining, his like 486 tower under his desk at home. It didn't scale, and it wasn't meant to. The next iteration was cleverly named V2, and that was a monolithic C++ application. The entire application of eBay was inside an ISAPI DLL. It grew at its worst to 3.4 million lines of code in that single DLL. They were actually hitting the compiler limits on the number of methods per class, which I'm ashamed to tell you that I know the limit at the time, which was 16K. So they were hitting 16K methods per class. So if you think you have a horrible monolith, like, this is definitely a horrible monolith. So they went through a next iteration, which they again cleverly called V3. That was a move from C++ to Java. I wouldn't yet call it microservices, but you could maybe call it mini applications. So the overall site was split into ultimately 220 different clusters that did, each of which did some of the pages on the site. So there would be a cluster that would be for the search capabilities, one for the buying capabilities, one for checkout, one for selling, et cetera, et cetera. And then there was a sea of shared databases underneath. The next iteration was a move to microservices written on Spring, but pre-Spring Boot. And then the most modern iteration of eBay's architecture is Spring on Spring Boot. Amazon has gone through a similar evolution, almost through the same time scale. So it also started in 1995, and the original monolithic implementation of Amazon was something called Obidos. It was a monolithic Perl and Mason front end over a C language back end. It was a 4 GB application that tried to fit in a 4 GB address space. You can imagine how much virtual memory swapping was happening there. They were regularly breaking the GNU linker on even trying to link the application together. It was so, I'll call it, effective at using memory that they had to restart the application every 100 to 200 requests because they were getting so many memory leaks. And because this was so monolithic and so kind of intertwined, Amazon was only able to release new code once every quarter. So that's not very sustainable. So from 2001 to 2005, they did a massive retooling of their architecture. They started building services in C++ and in Java. Those services were separate from each other, individual units, no shared databases. So Amazon was able to scale from there. And then the timing is not at all a coincidence. So immediately after they completed this migration in 2006, 2006, they started the first set of services as part of Amazon Web Services, and then they started their progressive takeover of the entire world's retail. So two stories, pretty different in detail, but pretty similar in outcome. So one lesson we can immediately learn is that no one starts with microservices, but past a certain scale, almost everybody is going to end up with microservices. So that's one aspect of simplicity, but I want to talk about 4 aspects here. So first I want to talk about simple components, and services are an example of that. Then I want to talk about simple interactions, so events and asynchronous communication between components. And then I want to talk about simple changes. As we're making changes to this system, that we make those changes in small and simple iterative steps. And then I want to put it all together and give you some examples from Amazon, from Netflix, and from Walmart. So first let's talk about simple components. So I like to start each of these with a little quote. So this is one from Tony Hoare. There are 2 methods of software design. One is to make the program so simple that there are obviously no errors. The other is to make it so complicated that there are no obvious errors. We'd like to be obviously in the first case, not in the second case. Okay, first aspect of keeping things simple is modular services. And we just saw those examples with the eBay and Amazon. And those service boundaries, we want to match our problem domain. And those service boundaries, we want to encapsulate both business logic and data. So this is what Amazon did really well in their retooling from 2001 to 2005. We want all the interactions to those services to come through the service interface and no kind of backdoor way of getting into the database from the back. And that interface is going to hide the implementation details of that service. And because we've put a boundary around that service, it allows us to encapsulate a lot of important architectural concepts and capabilities. So it's a fault isolation boundary. It allows us to do performance optimization within that service. And then also, critically in the modern world, it's a security boundary as well. So the next idea of making things simple is the code that we write inside that service itself. So what I'll call it orthogonal domain logic. So the domain logic that's the purpose of the service existing. So we want that domain logic to be stateless. We'd like to take a bunch of inputs, treat it as a pure function, and then produce outputs at the other side. And if we're able to do this, often a stateless implementation of domain logic really directly matches the domain that we're trying to model. If it's a pure function, it allows it to be deterministic and testable in isolation. We're going to see that later on in the talk. And then also it tends to be a lot more robust to change over time. And so what we want in here is what I'll call straight line processing. So within a service boundary, the code that we're implementing, the domain logic, should be just straightforward, very synchronous, minimal branching, very, very kind of like straight line. And then the orthogonal idea is that we want to separate that domain logic from all the input-output capabilities that we do within that service. So the ideas here, maybe people are familiar with hexagonal architecture or the ports and adapters pattern, or if you've come from the functional programming world, this is called functional core with an imperative shell. Okay, so that's the service, that's the logic inside the service. Now let's talk about making the data simpler. So the idea in the modern world is that we typically have systems that are so large they can't fit on a single machine, so we have to chop our data up into smaller pieces. That's called sharding. And shards allow us to partition what I'll call the data space of the application. So, and those shards in modern systems are units of distribution, so we can distribute them over different storage mechanisms. They're a unit of replication, they're a unit of processing, they're a unit of storage. And also, again, as these other things, is they're hidden as an implementation detail. So from the outside of the service, we shouldn't be able to tell that it's sharded at all. And again, those shards encapsulate a bunch of important architectural concepts, right? They give us resource isolation, they give us fault isolation, they give us availability guarantees for the individual shards, and they also allow us to perform a lot better. And then again, in modern cloud systems, those shards are auto-scaled. So we can divide the shards or scale out the shards as we need for either as our data grows or as our processing needs grow. And great examples are, DynamoDB partitions, segments in Amazon's Aurora system, tablets in Google's Bigtable. So this sharding idea is everywhere at large scale. So you say, well, that's great to make things simple, Randy, but I have a complicated application. How do I do that? Well, the obvious idea there is that we make individual services, but we compose those services in a large service graph. So common services that we leverage across a lot of different customer-facing services will implement widely used capabilities, and we have a service topology that looks like services that customer-facing services call shared services, which may be called other shared services, which call a platform at the bottom. And this is not really a layering, even though that's how I show it in the diagram. It's more like a computational graph. And the idea is that we want to simplify the concerns for the teams that are implementing those individual services. We want those teams to be able to concentrate solely on the business logic of their services and abstract away the details of the implementations of the services that are calling them and the services that they're calling. So it allows me as a service owner to focus only on the domain capabilities that I need to provide and leave the other capabilities that I need to other services. And so at the bottom, at these large-scale infrastructures, we end up having a common platform. So Netflix and Google are famous for having like a paved road. So there's a common set of implementation capabilities that all service teams are able to use, a set of shared infrastructures, standard frameworks, and it typically ends up making a lot simpler the developer experience. And again, the simplicity idea here is a separation of concerns between the domain things that we need to do at the service level and the platform and infrastructure capabilities that are provided by this common platform. And so, interestingly, at large scale, what I've observed in the big companies that I've worked at is large-scale organizations often invest more than 50% of their engineering effort in platform capabilities. Why? It's because as we have more teams and more engineers at the company, it's increasingly more valuable for us to invest in those common services and common platforms at the bottom, right? There's more return on investment. There's more leverage that we get from those platform investments as we get larger. So the service ecosystem tends to look like a set of customer-facing services at the top, a bunch of shared services in the middle, a bunch of platform capabilities at the bottom, and then there are often a bunch of what I'll call orthogonal capabilities like security and CI/CD, et cetera, that kind of cross all the boundaries. And then how do we evolve services in this infrastructure over time? So it's very similar to evolutionary biology. So we create and extract new services when there are new capabilities that we need. When services are no longer valuable, we deprecate them and have the team work on something else. And those services tend to grow and evolve over time. So a team might start out with one service, and then they might grow and split into two teams with two services, and it kind of grows like cellular mitosis in biology. And so there's so much creation of new services and deprecation of old services at Google. There's a phrase that people like to say, which is every service at Google is either deprecated or not ready yet. Okay, so that was simple components. Now let's talk about simple interactions. So again, the quote here is from Albert Einstein. We'd like everything to be made as simple as possible, but no simpler. So what do I mean? So the first idea of simple interactions between the components is the idea that those interactions ought to be event-driven. So as I'm changing the state of my individual service, I communicate those state changes as a stream of events to other interested parties, other services or other things that are interested in subscribing to those state changes. And an event in my world is a statement that something interesting has occurred, and ideally it represents a semantic domain event that is relevant for the domain that I'm trying to model in my service. Why are we doing this? We're doing this so that we can make my job simpler and the other team's job simpler as well. So we're trying to decouple the domains and the teams from each other. We've abstracted our interaction through this event system, and it allows us to be asynchronous from one another. So I can produce an event, and then another service or maybe several other services can consume that event and do something later on. And this model of taking in events, doing some processing, producing other events is a vastly simpler implementation of the component than other models that tend to be more synchronous. Another way that I can make my job simpler as a service owner is I can store my those state changes that I accumulate in an immutable log. So I want to store the state of my inputs and my outputs as an immutable log of events. This is called event sourcing. I'm sure everybody's familiar with that idea. But what's interesting is that it doesn't just help us from an implementation perspective. Modeling something as an immutable log of events often tends to map to the real world in a much more natural way than other data storage mechanisms. And if we're able to do this, if we're able to store our events in an immutable log, it allows us to encapsulate another set of important architectural ideas. So it allows those state changes to be durable because they're stored in the log. It allows them to be traceable and auditable. So if we have issues, as we always do in software's hard, we can trace and look back on what we did before and see why the output was that we got. It allows us to replay those events. So imagine we fix a bug. We can replay the events from a particular point in time and get back to a correct state. And also, it's super explicit and comprehensible about what has happened. So I can't tell you how many times I've had systems, where we've implemented a log-based storage, and we're able to diagnose and figure out what performance problems are happening or correctness problems simply by looking at the state of the world, looking at the state of changes. It's super valuable. And then, of course, the world isn't infinite, so as we are accumulating events over time, we want to compact those things into snapshots so that we don't have an infinitely growing set of storage. Okay. And the example here is from Stitch Fix. So Stitch Fix is a clothing retailer in the United States, and so the idea is that we would send people a box of clothes in the mail if they were a subscriber to the service. If they liked them, they would keep them. If they didn't, they would return them. So there's a very natural modeling of the state of one of these boxes in an immutable log of events. So in the beginning state is someone requests one of those boxes of clothes. We assign that box of clothes to a particular warehouse that's going to deliver it. It gets assigned to a human which decides what clothes should go in the box. That happens. Somebody goes through the warehouse and picks the items. We pack the items. They get shipped via a carrier to the customer. It travels as atoms through the real world, and then the customer ultimately, gets the clothes and decides whether he or she likes them or not. Anyway, this idea of those of a progressively accumulating set of events is super natural to the particular domain, and again, as I was saying, makes it hugely easier to debug issues that happen along the way. The last thing I want to talk about in terms of interactions is embracing asynchrony. So we want, if we're able to be event-driven, we're able to make the interactions between service A and service B asynchronous from each other, which allows us to first decouple the availability of A and B, right? So if A is up and producing events, B does not have to be up receiving events. B can come up later and receive those events later. Similarly, B can be up even if A is not up. So the availability of those two systems are decoupled, unlike what would happen if A needed to call B in a synchronous way. We can independently scale A and B as needed. Similarly, it allows us to do a lot more complex processing. So you can think of B as doing something in the background. So we could have something happen with A. We can immediately maybe get back to our customer. Then B can do some longer-term processing kind of in the background. And then, again, this asynchronous decoupling it makes it a lot safer for us to make changes to A and changes to B separate from each other. And again, it substantially simplifies the component implementation on both sides. So the last philosophical idea I want to make here is something that I want to set up, which we're going to talk about in detail with examples at the end, is the idea that if we have an event-driven asynchronous model between those services, we can often change something that starts out as a synchronous call graph into something that is an asynchronous data flow. What do I mean by that? So often, the way you might think of a set of interactions is A service calls B service, calls C, calls D, calls E. And all of those things need to happen in real time in order for A to get the answer that they want. Well, instead, there are lots of opportunities where we can have E produce events, which are then stored and enriched in D, which produces an events which go to C, which produces a set of events that go to B, which produces a set of events that go to A. And if we're able in this situation, and a lot of times that's a really valuable approach when there's a big difference between the number of writes that we need to do and the number of reads that we need to do. So if there's a big asymmetry between the number of writes and the number of reads, one of these this asynchronous model really helps out a lot. And so what happens along the way there is that we're actually joining the data, we're accumulating a bunch of events, we're joining the data into kind of materialized views along the way. And as we'll see in the several examples at the end of the talk, these can be systems that are implemented this way can be orders of magnitude less resource intensive, orders of magnitude better performance, and orders of magnitude more reliable. Okay, so we talked about simplified components, we talked about simplified interactions, now we want to talk about simplifying the changes that we make. And so here I want to introduce this quote from Gall's law. So a complex system that works is invariably found to have evolved from a simple system that worked. So the first idea here is that every change that we make to a system, we want to do incrementally in small units. So every large change that we might want to make, we want to migrate from system A to system B, something like that. We want to decompose that large change into small incremental steps. And each step along the way needs to maintain both backward and forward compatibility of the data that we are passing around and the interfaces that we have between the components. And so in a large-scale system where we're doing these incremental changes, it is a common case that there are multiple versions of an individual system in the overall ecosystem at the same time. So every change that we make is a rolling upgrade to existing systems, and it's transitional states between version 17 and version 18 of a particular service. Those are normal rather than being exceptional. So one of the ways that we can help make the system work and these simple tests, simple changes work well is by continuously testing the system. So by having a well implemented set of tests, it allows us to go a lot faster because tests are the solid ground underneath our feet that allow us to run really quickly. I actually took this picture at a CraftCon several years ago, so this is actually a tram here in Budapest. Tests actually make better code because it gives us the confidence to break things, it gives us the courage to refactor the system to make it simpler as we go along, and tests actually make better systems, so it allows us to catch bugs earlier and fail faster. So, but let's think about testing from the perspective of how does it make our jobs simpler and easier as developers. So Microsoft did a study a number of years ago that what do developers actually do every day? Well, it turns out that we spend 75% of our time reading existing code, we spend about 20% of our time modifying existing code, and we probably spend about 5% of our time writing new code. Well, if we have a well-implemented suite of tests, it absolutely helps us with these first two things, right? It helps us reading existing code. Why? Because tests are executable documentation. We can look at the tests to see how the code is supposed to behave. Obviously, the tests are there to help us with the 20% of modifying existing code. That's what they're there for. As we make modifications, we can guarantee that we haven't broken anything. It turns out that it also helps us with the writing new code as well, as we'll talk about in a second. So tests help us to make better designs because a more testable system is more modular. It's more everything that we would do to make a system easier to test, it would be separating concerns, making the individual units more simpler, more testable by themselves, and more encapsulated. So there's a great quote here from Michael Feathers. There's a deep synergy between testability and good design. All of the pain that we feel when writing unit tests points at underlying design problems. So the effort that we would put into writing tests is not just about the correctness of the system, although that's very important. It's actually about making the system easier to modify and making the system easier to build and design and to evolve over time. So an example in my background is at Stitch Fix, we were very disciplined about doing test-driven development. So before we implemented anything, we would write the tests, and only then would we implement the feature. And as a consequence, we basically didn't have a bug tracking system. Now, I'm not saying that we didn't produce bugs. We produced as many bugs as anybody. But we were able to maintain what I like to call an inbox zero of bugs, essentially because we had such a good suite of tests that we didn't have a big, long list of known bugs that we weren't ever going to fix. As a new production bug would come up, we would fix it, and then we would go on. And so we had a backlog of things that we wanted to do, but that backlog wasn't a whole bunch of bugs we needed to fix. That backlog was new features we wanted to build, and then technical debt, that we had accumulated intentionally over time. So the other idea here about making changes simpler is around canary deployments. So this is the idea of staging the rollout of a new version of a particular service. So if I have 100 instances of this particular service, I don't update all 100 at once. Maybe I update 1 and then 10 and then 20. Do a kind of phased rollout there. And this is enabled by a deployment system that allows us to do automatic rollout and rollback. That's a critical aspect here. But the idea here is that is that by doing canary deployments, by only exposing the new version, to a small number, a small percentage of the cluster, it makes deployments really routine and boring, and it allows us to find issues early and roll them back before they impact a lot of customers. So a canary deployment is about making deployments simpler by only changing a segment of a particular cluster at any one time. Feature flags are another dimension of the same idea. So, as you know, a feature flag is a configuration flag that allows us to enable or disable a feature for a particular set of users. And so the idea is that canary deployments allow us to sort of partition and successively roll out a feature or a new version over the cluster. Feature flags allow us to do the same thing over the set of users that we have. So again, by combining these two concepts, it allows us to make individual changes a lot simpler and a lot less impactful. So it allows us to build much more solid systems. So feature flags allow us to decouple feature delivery from code delivery. So we can successively roll out via that canary deployment a new version of our software, and then later at any point we can turn on that feature for a particular set of users and more users, et cetera. So and because this is a flag, this allows us to do this rapidly on and off. It allows us to do a lot of good experimentation where we can separate experiment groups from control groups. We can experiment on new features as we're building them, and then it allows us also to develop and test and verify our code in production. So if we combine these ideas, we're at continuous delivery. So it allows us to deploy services multiple times a day. And that also allows us to build much more solid systems. So it allows us to release smaller, simpler units of work. The incremental changes that we're making are a lot easier to roll back and to roll forward. Because they're small, the changes are smaller, it makes it faster to repair when things go wrong. It makes it easier to understand what's changing about the system. It makes it simpler to diagnose problems. And also, because we've made the changes smaller and simpler, it actually allows us to increase the rate of change that we make to the system without increasing the risk of the change. Again, making smaller units of changes is a lot less risky than big changes. And so the work that I did most recently at eBay, where I was chief architect, was leveraging a bunch of these concepts to make the deployment system and the deployment capabilities of eBay services a lot simpler. So I led a cross-company initiative, which we called the Velocity Initiative, which is around improving the software delivery capabilities, so making it much more repeatable and fast and more robust and a lot faster. So the idea, again, in taking big problems and making them small, we were iteratively identifying and removing bottlenecks to software delivery. So we would go to individual teams and we would say, hey, it looks like you're releasing your software every 3 or 4 days. What if I told you had to release your software every day? Tell me all the reasons why you can't. And they would say, how much time do you have, Randy? Here's a long list of all the reasons why we can't release faster. And I would say, great, the platform team works for me, and so you just gave us our backlog. Does that make sense? Tell me all the reasons why you can't go faster. Point. Great, we'll just go down and help you with all those. So, and again, that concept of there is making a big problem of improving software delivery performance into a series of smaller problems. Well, let's fix this problem with the build system. Let's fix this problem with the code review system, et cetera, et cetera. And as a consequence, we were actually able to double the engineering productivity of the teams that we worked with. So given the same team, they were able to produce twice the number of features and bug fixes than they were before. And then if we want to look at the DORA metrics, we were able to improve our deployment frequency, how rapidly we were able to deploy by 5 times. We were able to get 5 times shorter lead time. We were able to reduce the change failure rate and then reduce the mean time to restore. So all these things, again, by making the deployment system a lot simpler. And the reason why I did this as chief architect is the ability to make small, repeatable, robust changes to the system is a prerequisite for trying to make large-scale architectural changes across the system. All right. So we talked about simple components, we talked about simple interactions, and then we talked about simple changes. So now let's put it all together with a couple of worked examples. So the first example here is actually from Amazon Aurora, which is AWS's one of their database systems. And the typical way that a distributed database system would work is that as we accumulate changes in the database, those changes would be two-phase committed around the different elements of the cluster, right? So there would be a consensus round, maybe with Paxos or two-phase commit or with Raft, and all the different components of the distributed of that storage system would have to do a round in order to move forward in every step. That's pretty painful and makes it actually really difficult to scale distributed databases. So the beauty of the Amazon Aurora approach is kind of like what we talked about earlier, which is trying to invert that synchronous Paxos round into something that's more asynchronous communication between the individual components. Okay, so those redo log writes, those changes that are made to the database system, are actually sent asynchronously to all the individual nodes, and they're acknowledged asynchronously back to the leader. And there's actually no distributed consensus round here at all. Instead, there are asynchronous, immutable, and monotonic changes that are broadcast out from the leader to the followers, and then the responses come back asynchronously. So instead of doing one of these consensus rounds, the state of the system, the database system, moves forward by quorum acknowledgement. So the individual storage nodes are replying back to the leader, and the log progresses forward when a quorum, when a sufficiently large number of the components have responded back. And so the only time that there's any distributed consensus rounds run at all is when is in the non-normal case of crash recovery. Anyway, so Amazon Aurora, way deep in the bottom of these database systems you might be using on AWS, implements these ideas that we've been talking about. So let's talk about the same idea from Netflix. So the example here is the viewing history of Netflix. So the idea is that people are watching movies on Netflix, and Netflix is accumulating a bunch of data about the watching behavior of all the customers. So you can imagine that data is pretty large. So as of several years ago, Netflix was receiving 1 million requests a second from this as part of this service. And they use that viewing history for tons of different things. So they're obviously using it for when I want to go see what I viewed, but also for personalization, for recommendations that they would make, analytics. There are lots and lots of different use cases from this log of viewing history. So the original synchronous architecture was all those million requests a second being written directly to the persistent storage and directly to a lookup cache for these other use cases. As you can imagine, that might work well in lots of cases, in in the standard situation, but when Netflix was under high load, there was a lot of back pressure. They would lose a lot of data, and they would get a lot of unavailability of this particular service. So instead, what they did is they inverted the architecture to be a lot more asynchronous. So instead, as in the diagram, the playback data is going into durable queues. Those durable queues are being processed asynchronously, and then an asynchronous pipeline enriches the data, processes it, and is able to do a bunch of those different use cases, right? So the recommendations use case, viewing history, et cetera. And then, as I mentioned before, those other services and other capabilities would materialize the views of the data that they needed by joining together the data from the viewing history with other data that they had before. And that allows it to, and that allows the reading side of the system to be asynchronous from the writing side of the system. Okay, so the last and maybe the coolest, I think, idea here is something that Walmart did around item availability. So what is the purpose of item availability? It's asking the question. So when you go to the Walmart website to buy something, it's asking the question: is this item available to ship to this particular customer? And so you can imagine that the SLO for the customer facing this is pretty harsh. So they wanted to get 99.98% uptime in a maximum of 300 milliseconds. So as you might imagine, if you've ever worked in an e-commerce environment, there's a lot of complex logic that goes into deciding whether this item is available to ship to this customer. So is this item available in inventory? Where is it? What warehouses is it available? Are there reservations on those items? Are there back orders on those items? Is that item able to be eligible to be sold in this particular country or this particular region? Are there sales caps on that item, et cetera, et cetera, et cetera? So it turns out that in the original synchronous architecture, I'll show you a diagram in the next slide, was a graph of 23 nested synchronous service calls that were all in the hot path. In other words, when Walmart was trying to show an item to a customer whether the item was available or not, there would be 23 nested service calls that were associated with getting that yes or no response. Any one of those 23 components, if it failed, would completely invalidate the results. The results would be wrong. So as a consequence, if you do the availability math, for those 23 components, they needed each of them to be 5 nines of availability, so 99.999% available, with a 50 millisecond marginal latency. And so as you can imagine, that system was extremely expensive to build, extremely expensive to maintain, and wasn't as reliable as it could be. Okay, so this is the diagram. This is the architecture diagram about that. And the details aren't important. Just notice that there are a lot of boxes and there are a lot of red lines. So the boxes are the individual services. The red lines are all the calls that need to be made in the hot path, just simply to answer the question: is this item available to ship to this particular customer? Okay, so what they did is they inverted each service in the way that we've been talking about, inverted each service from a synchronous call graph into an asynchronous data flow. So the systems that were, the ultimate systems that were actually parts of the system that were actually changing. So as things went into and out of warehouses, as an example, those things would produce events which would be consumed by other services and and joined together with other data that they had, which are consumed by other services, joined together with the data they had, and made available to the top of the system. I'll show you an architecture diagram of this in the next slide. All of the processing was idempotent, so if the events were sent multiple times, it wouldn't change the result. Each of those individual systems along the way maintained their state as an event-sourced immutable log, and they maintained, as we're seeing over and over again, a materialized view of that data. So this in this asynchronous re-architecture, instead of having 23 services in the hot path, there were 2. Those async services, instead of needing 5 nines of availability with 50 millisecond response time, instead they were only needing to have 3 nines of availability, 99.9%, and the latency could be in seconds or even minutes. it was, as you can imagine, this would be much more resilient to delays and outages of those changes happening, and it was orders of magnitude more reliable and simpler to build and operate. So this is what the diagram looked like after the re-architecture. So again, the details aren't important. Simply note that there are many fewer yellow boxes, and there are many, many fewer red lines. So so once they did this asynchronous re-architecture, in order to answer the question, is this item available to ship to this customer, all they had to do was call an API which called a particular data store that had that capability, or had that data there. Okay, so big improvement by making the system a lot simpler. All right, we've made it. So we talked about simple components. We talked about simple interactions, we talked about simple changes, and we put it all together with a couple of examples. So I think I have some time for questions, but thank you very much for listening.
Thank you so much, Randy. We have a question that just came in to Slido, and we're going to put it up here.
Okie doke.
How do you represent these systems in enterprise architecture service management tools? Any examples of good application portfolio management for microservices?
Oh, wow, that's a good question. No, Adam, but maybe we should talk later about that one. To be honest, I've never seen a comprehensive service catalog implemented at any particular place that's really, really good. As a practical matter, even in really large-scale organizations, the way you find out about other services is by talking to your friends. I've seen a bunch of service catalogs, but I haven't seen anything that's like an application portfolio management tool. So it's a great question.
We have time for just one more. Would you like to choose which of those questions that we go with?
We can just go in order. Okay. Monolith is easy to grasp. It's difficult to grasp the entire code base for microservices. This is not a problem. Well, overall, the system is complex in all those cases. It's easy to know. In a monolithic system, I appreciate that it's easy to know where the problems are. It's in the monolith, because there's no other place. It turns out, though, that over time, at large scale, breaking the system up into smaller units allows any individual person to only need to concentrate on a small particular part of the system. So while the overall system does the same things that it did before, interestingly, by chopping it up into smaller parts, my experience has been that it makes it a lot simpler. It's simpler to implement those components, it's simpler to know where the issues are, and it's simpler to change them. So that's been my experience.
Thank you so much.